feel the vibe.
What's up, guys? It's Mr. Gaines here again, taking a look at another Algebra 2 instructional lesson as we start to expand on what we learned about on polynomials the last time you guys were on as a viewer, and we are going to get into zeros and graphs of these polynomial functions. Zeros and graphing of polynomial functions relies on the fundamental theorem of algebra, essentially the backbone for everything that we do in algebra. So the fundamental theorem of algebra tells us that if we have a polynomial and it has a degree of 1 or more, so you're going to have an x to the first power or to the second power or anything greater, as long as those polynomials have complex coefficients, then the polynomial is going to have at least one complex zero. So if it has a degree of 1 or more, it's going to have one complex zero or potentially more. This is something that you've kind of already addressed in Algebra 1 and Algebra 2 up to this point this year, but we're going to go ahead and we're just putting it down into an actual formal written presentation as to the focus of where we progress with polynomials. So in problem number 1, it's going to tell us to break these polynomials down into a product of linear factors. Remember when we solve equations, let's I'm going to throw an example up here on the screen. Let's say x squared minus 2x minus 1 is a polynomial. It's a quadratic. Sorry, let's not make this minus 1. Let's make this plus 1. If you wanted to factor this, to solve it, to find the solution, you'd set it equal to 0. You'd probably break this down into x plus 1 quantity squared, x minus 1 quantity squared, square root 0 to get x minus 1 equals 0, and you'd find the solution x equals 1. So you'd find that it has at least one complex solution here that came from a product of linear factors. Well, we can do the same thing with any polynomial. We can break this polynomial down into a product of linear factors, which is going to allow us to find its zeros rather quickly. So if we take a look at problem 1a, this is a quartic function, a quartic polynomial, because it's x to the 4th power. Quartics occasionally can be factored like quadratics. Notice that this is an x to the 4th power with an x squared middle term and then a constant. We can factor this again like we would a quadratic into two binomials. Now as we factor this, this is going to become x squared and x squared as my initial terms in each grouping, because what I want is I want to distribute x squared to x squared and get an x to the 4th. Also through distribution, I need a negative 8x squared, so I need both of these terms to be x squared. Now I know the second term in each has to multiply together to give me a negative 9. So I know that one has to be a positive value, one has to be a negative value. I'm looking for factors of 9 that are going to work, and we would see that positive 1 and negative 9 would work. So if I were to distribute to check this, this would be x squared, negative 9x squared. You add those together, and that does give me a negative 8x squared. So I have factored this a little bit further. Now, it wants a product of linear factors. Remember, linear factors are when we have x to the 1st power, not x to the 2nd power. So I need to factor this a little bit further. Notice that I have a sum of 2 squares and a difference of 2 squares. So I'm going to take us back a little bit on something that we learned earlier this year. Factoring polynomials that were a sum of 2 squares. We can do this using imaginary numbers. Remember, x squared plus 1 is the same as x squared minus I squared, or 1i squared, because I squared is negative 1. So a minus negative 1 is the same as a positive 1. The reason that I did this was because now it breaks this equation down, or rewrites this equation as a difference of 2 squares. And any difference of 2 squares can be written as a product of the conjugates. So if I want to factor x squared minus I squared, this would be x minus I and x plus I, the conjugate of the root of both of these terms. I can do the same thing with x squared minus 9 and get x plus 3 and x minus 3. So this would be p of x written as a product of linear factors. Each one of these terms, or each one of these binomials, are all linear, and they would multiply together. If we wanted to reverse the process and go through distribution, they would multiply to give us x to the 4th minus 8x squared minus 9. So if we can factor in this instance, we want to. Let's go ahead and take a look at q of qx, 1b. We aren't going to factor this in the same method. This one is a cubic function because it has an x to the 3rd power. So it's not going to factor into two binomials. What we may notice about this cubic function is that it has 4 terms. So we might remember that to factor these, I can try to group. So I'm going to group the first 2 and group the second 2. I'm going to take the GCF out for the first grouping, which would be an x squared, and that's going to leave me with x plus 2. I'm going to take a GCF out of the second group that I want to leave me with x plus 2, and that would be negative 4. So this would leave me with x plus 2 if I factor out a negative 4 from the second group. Remember, the coefficients become a factor. So x squared minus 4 times x plus 2. And this is a problem that this type of problem is one that we saw on our Unit 3 test, where we were able to factor a cubic by grouping, and while doing so, we end up with a difference of 2 squares, which we can factor further. So we want these again to be all linear, so this would end up being x minus 2 and x plus 2 as a conjugates of the square roots of these two terms, because it is a difference of 2 squares, and then another x plus 2. So I'm going to go ahead and write this out as just the product of the 3 linear factors, not worrying about writing x plus 2 squared just yet. You could. So the goal here is to factor these completely until we get down to all of the linear factors. Now notice here that in p of x, we started with a quartic polynomial. X to the 4th power, the highest degree was 4. There are 4 linear factors, some imaginary, some real, but 4 linear factors. In B, we had x to the 3rd power. It had 3 linear factors. If the example that I showed before, let's say it was x squared minus 2x plus 1. When we factored that, it was x minus 1 squared, or x minus 1 and x minus 1, which has 2 factors. Notice that matches up with the degree of the polynomial, or the highest exponent. This is consistent for all polynomials that have real or complex solutions. So the linear factorization theorem tells us that if we're given a polynomial p of x, which could be written as we had here before, I'm not going to write that all down again, but if we had p of x with degree greater than 1, a degree of n greater than 1, so it could be, greater than or equal to 1, so it could be 1, 2, 3, 4, so on and so forth, that polynomial will have n linear factors. So if it is of degree 3, it's going to have 3 linear factors. If the polynomial is degree 8, it's going to have 8 linear factors. If the polynomial is of degree 112, it's going to have 112 linear factors. This will be true for all polynomials that we are going to factor here in Algebra 2. So let's progress again a little bit further with an example here. It says in problem 2, factor each of the following functions completely, and this time writing repeated factors in exponential form. So if we have a factor that shows up more than once, we're going to write it as a squared value. If it shows up twice, if it shows up 3 times, we're going to write it as a cubic value, so on and so forth. So the first thing that I'm going to take a look at is I'm going to figure out what the degree would be for this polynomial. So let's say I were to try to distribute and multiply everything out. Eventually through distribution, I would get x squared times x squared, which would be x to the 4th, and I would get this x to the 4th times x, which would be x to the 5th. So this polynomial, if I multiplied everything out, would be of degree 5. So what we know is when we factor this thing, if we factor it completely, we should have a total of 5 linear factors. So let me factor this first piece. So x squared plus 8x plus 16, this is a quadratic trinomial. So I'm going to try to break this down into two binomials. This would be x times x, which would give me x squared. Factors of positive 16 that would work would be positive 4 and positive 4. So if I checked it, 4x plus 4x would give me an 8x. So my first grouping there factors into x plus 4 and x plus 4. My second grouping, I'm going to go ahead and change colors for my second grouping, would also a quadratic trinomial. I'm going to try to break it down into two binomials. So x and x would give me x squared. Factors of negative 20, and know one's positive and one's negative. The factors 4 and 5 would work, x minus 5 and x plus 4. And then finally, at the end of this, I have the x minus 5 that it originally gave us, which is a linear factor. So now if I count these linear factors, I see, yes, there are 5 linear factors. 1, 2, 3, 4, 5. And here it said to write the repeated factors in exponential form. So P of x has the factor x plus 4. How many times does x plus 4 show up? 3 times. So x plus 4 is being cubed. It also has the factor x minus 5. How many times is x minus 5 showing up? 2 times. So it would have the factor 2. That quantity would be squared. So if I wanted to check the degree here, I'm going to get an x cubed from this cubic value here. I'm going to get an x squared from that squared value here, and then the x cubed times an x, so it would end up getting, for degree, x cubed times x squared, which would give me an x to the 5th, or a degree 5. So this is my polynomial, completely factored and then written with the repeating factors in exponential form. So we can use some of the factoring techniques that we've learned in the past to break polynomials down into linear factors. Now, what if things don't factor nicely, or we don't have techniques to factor them? This is where a method that we learned, or we're going to learn now, in combination with the factor or root theorem, factor or remainder theorems, are going to allow us to fact pretty advanced and complicated polynomials. So the rational root zeros theorem, we're just going to focus on this and then see how it's going to help us to factor. The rational zeros theorem says that if we're given p of x, a polynomial, with p as a factor of the constant and q as a factor of the leading coefficient, all rational zeros will be of the form p over q. So p is a factor of the constant at the end in standard form. Q is a factor of the leading coefficient in the beginning of standard form. And then all rational zeros come from p over q. Now let's see what that looks like with actual numbers in an equation. So for 3, we're not solving anything. We're just listing possible rational zeros. We're not figuring out which ones are zeros. We're just establishing a list of possible zeros. The reason that we do this, if I take a look at 3, I might see that this is a quartic, and I might want to break it down into two binomials, but it's not a trinomial, so it's not going to factor that way. There's 5 terms here, so unless we do some pretty impressive manipulation to this equation, we're not going to be able to group it. So we need to be able to establish kind of a list of possible things that could be zeros, which will eventually help us to factor. So P and Q are what we're gonna focus on, and you'll see me talk about P over Q. So P would be the factors of the constant at the end, negative 24. So factors of negative 24 would be 1 and 24, 2 and 12, 3 and 8, 6 and 4. Remember, you can find these on the calculator by taking 24 and dividing this by x, the number that we're looking for factors of, and dividing it by x. Then we can go ahead and we can look at the table. The table will show us any combination of numbers that are going to work here. What I might do here for this one is put a negative in front. Now I'll go ahead and look at the table. So -4 and 6, -3 and 8, -2 and 1, -1 and 0, or sorry, -1 and 24, 0, no, doesn't work, 1 and -24, 2, -12, 3, -8, 4, -6. And then we'll see that either numbers repeat or are decimals after that. So the reason I put the negative in front is so that we can see that the 1 could be a factor if it's positive, or the 1 could be a factor if it's negative. So really, the factors of P are positive and negative values of 1, 2, 3, 4, 6, 8, 12, and 24. So P would be any of this set, positive or negative values of 1, 2, 3, 4, 6, 8, 12, and 24. Q is going to be a smaller grouping. Q is factors of the leading coefficient. And our leading coefficient is 3. So we could either have +1 and +3, or -1 and -3. So plus or minus 1 or and 3. So my possible rational zeros for the polynomial are P over Q, or any of these numbers in a fraction over any of those numbers. So my possible rational zeros I'm going to list as P over Q. It would be 1 over 1, which is 1. 2 over 1, which is 2. 3 over 1. 4 over 1. 6 over 1. 8 over 1. 12 over 1, and 24 over 1. Then all of these numbers over 3. So 1 over 3, which is just 1/3. 2 over 3, which is 2/3. 3 over 3 is just the same as 1, so I'm not going to rewrite that one. 4 over 3. 6 over 3 is 2. I already have that in my list, so I'm not going to rewrite that. 8 over 3. 12 over 3 is 4. That's already in the list. I don't need to rewrite it. And 24 over 3 is 8. That's in the list. I don't need to write it. So we cannot factor f of x. If I wanted to find rational zeros, so real numbers, whole numbers, or numbers that can be written as fractions, one of those numbers would have to come from the list. Okay, so I could find the zeros of here, and we're going to get there eventually, but the zeros would be one of these numbers. Now, if you remember the rational roots, or sorry, if you remember the factors and remainders theorem, to find a zero, I can substitute these numbers into f of x. So if I pick a number from this list and substitute it into f of x, and it works out to equal 0, then that number is a 0. So what it does is it basically reduces our answer from all rational numbers, so all the way to infinity and negative infinity in both directions, down to a list of numbers that could potentially be zeros for this function, and this would be the inclusive list. Let's go ahead and take a look at another problem using the rational zeros theorem. In 3b, we're going to do the same thing. So we want to list the possible rational zeros. So P is factors of the constant, 15. So this could be plus or minus. We're going to find out that all of these cases are going to involve both positive and negative units. So plus or minus 1, 3, 5, and 15. Those are the only factors of 15. Q would be factors of the leading coefficient. So in this case, plus or minus 1 and 2. So my possible rational roots would be P over Q. So all of these numbers that are in the list of P over each of the numbers in the list of Q. So 1 over 1, 2 over 1, sorry, 1 over 1, 3 over 1, 5 over 1, 15 over 1, then 1 over 2 or 1/2, 3 over 2, 5 over 2, or 15 over 2. Any of these positive or negative versions of these numbers could be possible rational roots. or possible rational zeros for h of x. If you get in the concept at this point, go ahead and pause the video and see if you can find the possible rational roots for r of x listed in C. Hopefully you got a chance to do that. So again, it's going to be P over Q, where P is the factors of the constant 36. So 1, 2, 3, 4, 6. I don't need to list 6 again, so just once. 9, 12, 18, and 36. Q would be our possible rational zeros for the leading coefficient, which is, possible factors for the leading coefficient, which is 7. So if I list those, 1 and 7. So my list for the possible rational zeros for r of x would be P over Q, which would be 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 9 over 1, 12 over 1, 18 over 1, and 36 over 1. And then all of these numbers over 7. 1 over 7. I'll go ahead and close this set and start a new set. I need a little more room here. Then continue with 2 over 7, 3 over 7, 4 over 7, 6 over 7, 9 over 7, 12 over 7, 18 over 7, and finally 36 over 7. So this would be, this entire set, P over Q, would be the possible rational zeros that could exist for r of x. So again, what this allows us to do is find a list from all rational zeros, all rational numbers, to a limited value that could exist as zeros for a function. This is a good place to stop with polynomials. We will continue taking a look at those zeros of polynomials and then get into graphs of polynomials. As always, thank you guys for tuning in, and I'll see you soon.